You know, when you look at something incredibly complex, like a brand new car or one of those high-tech factory robots, have you ever really stopped to think about how it came to be? Today, it's about a whole lot more than just wrenches and paper blueprints. It's about building in a digital world first. Welcome to the world of simulation-driven design, and trust me, it's changing absolutely everything. So, let's put ourselves in an engineer's shoes for a second. This is the question that keeps them up at night. You have a brilliant idea, right? But building a physical prototype costs a fortune. And if it's wrong, well, you scrap it and you start all over again. And maybe again. So much time, so much money, down the drain. There has to be a better way, doesn't there? To find it, we first have to really understand the problem they're up against. And that problem, well, it actually has a name. It's called the engineer's dilemma. And it's a paradox that complicates every single design project right from the very beginning. Okay, this slide just lays it all out. It's a real catch-22. Think about it. Right at the start of a project, you have total freedom. You can change anything and everything on a whim, and it's super cheap to do. The problem? You're basically flying blind. You have almost zero knowledge about what's actually going to work. Now, let's fast forward to the end. You've built things, you've tested them, and now you know exactly what you should have done. You've got all the knowledge, but try to change something now? Forget about it. It's insanely expensive, if not totally impossible. So what's the solution? Well, this quote from Johann Wall really nails it. The only way to crack this paradox is to somehow get all that critical knowledge, all that experience, way earlier in the game when your freedom to make changes is still high. But that just leads to another question, right? How can you experiment on a machine that doesn't even exist yet? Well, this is where the magic happens. You build a virtual twin. You create the entire machine, bolt for bolt, wire for wire, inside a digital environment first. This lets you experiment with it, break it, and perfect it, all before a single piece of real metal ever gets cut. In the engineering world, this virtual twin is called a model. And this definition here is key. It's not just a 3D drawing. It's a living, breathing mathematical representation that's designed to behave exactly like the real thing. It's a tool for understanding and, here's the most important word, for prediction. And here we can see that idea perfectly. On the left, you've got a physical, real-world automotive exhaust system. You can touch it. On the right, that's its virtual twin. It's pure math living inside a computer, but it knows everything. Its shape, its materials, and exactly how it's going to vibrate and react under stress. So why go through all this trouble? The advantages are just massive. I mean, you can test thousands of different designs in a single afternoon. You can push the virtual machine to its absolute breaking point without any actual damage. You can fine-tune every little detail for peak performance, and you do it all before you even start thinking about a factory. The amount of time and money this saves, it's incredible. It's a total game changer. Okay, but a model of the machine's physical body is only half the story. To really simulate it, you need to give it a brain, a control system that tells it what to do. And this is where we see two really different ways of thinking. First, you've got what's called an open-loop system. Think of it as the dumb control. The boiler example here is perfect. A simple timer tells the boiler to turn on at 6 a.m. and off at 8. It does its job, but it has no idea what the actual temperature is. It's just blindly following orders without any clue about the result. But then you can build something much smarter, a closed-loop system. Here, you add a thermostat. Now the system has senses. The thermostat is constantly checking the room's temperature, and this is the critical part, it sends a feedback signal back to the boiler. If it's too cold, it tells it to work harder. Too hot, it tells it to shut off. That feedback loop is everything. It's what allows a system to be intelligent and self-regulating. Okay, so we've got the theory down. We have a virtual body, and we have a smart virtual brain with a feedback loop. Now let's see how engineers put all of this together to design a seriously precise, real-world machine. Our case study is this impressive piece of gear, an industrial water jet cutter. This thing uses a super high-pressure stream of water to slice right through hard materials like steel. For it to do its job, it has to be unbelievably precise and stable, with absolutely no unwanted vibrations. So how do you make sure your computer model acts just like the real machine? You have to get real-world data. Engineers will literally attach sensors to a physical prototype and use shakers to see exactly how it vibrates in response. This gives them their ground truth, their benchmark for reality. And this chart shows the ultimate goal. It might look a bit complex, but the idea is actually simple. You're trying to make the simulation match reality. At first, the data points are all over the place. But then, the engineers start tweaking their virtual model, adjusting the stiffness here, the mass there, until the simulation's predictions perfectly line up with the real-world data. That perfect diagonal line means you've done it. Your virtual twin is now a true digital replica. And this is why that whole process is so crucial. Once that model is validated, it's not just a guess anymore. It's a predictive tool that you can trust. Engineers can now confidently use this virtual twin to test wild new ideas, knowing that the simulation results are going to reflect what happens in the real world. This process is already incredibly powerful, but there is one final step, one amazing technique that brings everything together and completely solves that original engineer's dilemma we talked about at the start. It's called hardware in the loop, or HIL simulation. And this is where things get really clever. Instead of simulating both the machine and its controller, you take the real physical controller, the actual computer that will run the final machine, and you plug it into a real-time simulation of the virtual twin. Let's break that down. The real controller sends out a command, maybe move the cutting head. The virtual machine model then calculates in real time how the physical machine would have moved. Then it generates fake sensor data, simulating what the real sensors would have reported, and sends it back to the controller. The controller has no idea it's not connected to the real thing. This lets you do exhaustive testing of the machine's brain before its body even exists. And that brings us to the final triumph. Hardware in the loop closes the loop for good. It completely solves the design paradox by giving engineers near-perfect knowledge of how the entire system, the mechanics, and the electronics will work together right from day one when their design freedom is at its absolute highest. So by building, testing, and perfecting our most complex machines in a virtual world before they ever become reality, we've fundamentally changed the pace of innovation. Which leaves all of us with one really thrilling question. Now that we've solved the engineer's dilemma, what incredible new machines will this power unlock in the years to come?